Today I'm going to talk about load balancing in cloud web services. So everyone knows that load balancing is to distribute workloads across different servers so that we achieve optimal resource usage. In this paper, we particularly focus on multi-class workloads so that users can have like a gold, silver, bronze level services, and these users can have differentiated service level agreements. The objective is to maximize the system revenue, which is equal to the weighted throughput, and to achieve optimal resource usage. This table summarizes the common policies used in the most popular cloud. And this policy we consider here as a random, round-robin, weighted round-robin disconnection, and the source-based load balancing. And we can see that the round-robin is the most popular one in the cloud. And its weighted version, the weighted round-robin, is also adopted by many of the infrastructure as service providers. Therefore, in this paper, we will consider mostly for the weighted round-robin policy. This policy is able to feature heterogeneous resources in the cloud, so that the more weight you assign to a server, the more workload the server will have. Like the challenge is that how to assign these weights. We will show in the next slide that naive weight assignment, such as you assign weight according to the number of cores for each server, is not very efficient. The idea in this paper we use is to use probability to represent weights so that we can build stochastic models of the system to obtain the theoretical optimal probability. Then the rest of the problem is to see if the probability is routing is the same as the weighted round-robin. Here we present the motivating example. So it's compared from the naive weight assignment to the given theoretical methods. The first one is assign weights according to the number of cores, and the second one is according to ECUs. The ECU is an index used in Amazon EC2 to assess the computer capacity of the machines. And the other two are the given theoretical methods. In the figure, we can see that the y-axis is the revenue. We can see that the theoretical method is better revenue than the naive weight assignment. This is encouraging, so we can try to see if we can use theoretical values to assign in the real-life system. This is the community network model we use to extract a typical web service system. The daily server here represents users sending requests to the application servers. The application server has a parallel topology, and we assume that the database is co-located with the application server. The load balancer will send requests to the application server according to probability P here. And we assume there are in total n servers, and there are clusters of users. In addition, we also assume that it's a closed network model, so that there's a fixed number of users running the system. The objective is to maximize this revenue, which is equal to the weighted throughput. Service rate is a very important parameter for queue network models. It characterizes the processing speed for the server to process each type of requests. Here we use a complete information algorithm to estimate the service rate. This algorithm requires both arrival and departure timestamps to do the complete trace analysis, and is able to return the near exact value of the service rate. Now we'll present the two theoretical methods. The first is the optimization method. It's very simple and straightforward. So the objective function is to maximize the system revenue. So the objective condition is that the first one is that it has to follow a queue network law, and the second one basically means that the probability has to sum to 1. The HR here means that the all the requests of R can only go to the servers belong to the HR. After we solve this program, we can obtain the optimal routing probability by the Lot's formula. Another theoretical method is the heuristic method. It's a heuristic solution to optimization program to require additional parameter n here. So the algorithm goes as following. So that the first step is to see for each server which class returns the maximum weighted service rate. If it's a heavy load system, we can assume that if it's the highest weighted service rate, it normally returns the highest throughput. Therefore, server from the input parameter m to the capital N, we obtain the routing probability for each server. Now we just the rest of the request to the rest of the servers. To understand better this algorithm, we present a simple example. So we assume there are 4 servers in the system and 3 classes of users. The input parameter n is choose to be 2. Then the first step is to see for each server, which class returns the highest weighted service rate. Then we go from the n equals 2 to do 1 by 1 to see for each server. We can see the 4 class 3, the server 2 and the server 3 both have the weighted service rate of 0.8. Therefore, we'll assign the equal probability for the both servers for class 3. Now we can see the server 4 has the highest service rate of the class 2. Now we assign this one to the service for server 4 to the class 2. Then we assign the remaining or the request to the rest of the server, which is server 1. The advantage of both the optimization program is that it works for different levels of workload. However, it requires like the additional parameter like the total number of users for each class, and is computationally expensive. It also shown that it achieves poor performance for large systems. On the other hand, the heuristic algorithm is computationally efficient and is able to achieve the optimal result when the number of servers n is large. The only disadvantage is that it only works best for the heavy load. So the remaining job is to see if we can use probability to assign to the weighted robin algorithm. Here is the experimental setup. So we have workload generator general request to the servers, and we use the multi-host monitoring system to monitor the servers. So we choose the arrival and departure timestamp of each request. The application we use is Apache Speeds, and the hard proxy is the load balancer. We deploy every component on Amazon EC2. Here is the instance type we use used. This is the deployment of each component. We should focus on the 4 off-peaks here. We can see the first way has the same type, and the last one has additional, which is like 2 cores, and it has more computing power. The problem of the theoretical method is that only works for single core server. Or you can see in the previous slide, we deploy the server on the 2-core machine. Therefore, we propose 2 methods to solve this problem. The first method is to assume that each core is 1 server. Then we run the theoretical methods and obtain the writing probability for each core. Then we sum the writing probability for each core to get the writing probability for each server. The second method is very straightforward. The CI is the number of cores. We just calculate the service rate by times the number of cores. This figure, the left figure shows the revenue and the right shows the CPU. We can see the second method is able to return higher revenue, and utilization is more balanced. Therefore, we always use the second method for the other experiments. The 4 load balancing processes we consider here are the same as the motivating example. So it's proportional to the cores and CPUs and the 2 theoretical methods. So first we want to see if we use the probabilistic routing in the same method which are round robin. We here use like 2 classes of users and set them in the off bench, which is the workload generator. Here is the revenue of the probabilistic routing and which are round robin. We can see that the optimization program returns always the best revenue in all the cases, and overall they are quite similar. And if you look at the response time, we can see that for both station 1 and station 2, here they have similar, in both cases they have similar response time. Therefore, we can see that to assign the weights from the probability to the weighted round robin is possible. Now we extend the experiment to consider 4 classes of users. So we can see it has more requests while one session is different. This time we only consider weighted round robin policy. From the revenue, we can see the optimization program still returns the best result, and the heuristic is also better than naive weight assignment. method. The CPU is also quite balanced for the optimization program. And for the response time, we can see it's still quite similar result as the two users case. If you look at all the 4 sessions here, you can see roughly the optimization and the heuristic is roughly good. Therefore, the conclusion is that overall the property routing returns a similar result as the weighted round-robin policy, and setting the weight of the weighted round-robin from the property is possible. In overall, the optimization returns the best revenue, and the heuristic also gives better results than the 9 weight assignment methods. And that's all. Thank you.
You mentioned computational expense several times. I wondered, in practice, would you simply produce a lookup table or cache so that you wouldn't need to do this calculation? Is it feasible just to store the answers and look them up?
You mean to show the computer time? Or
you mentioned your algorithm was computational expensive.
Yes.
I wondered if it would be feasible to run the computation offline and then simply look up the answers.
Yes, it is possible, but the problem is that the system always adapts at runtime. So actually the future work is to see the runtime adaptation of the system. So we can see the load balance, maybe stretch changes all the time as the users maybe change. The problem of the optimization program is that it's optimization program. Therefore, it takes quite a long time to find the solution. And sometimes if you find maybe it's block optimum, maybe you need to run many times to see which is the actual value. But for a heuristic algorithm, it's very straightforward. It takes like 5 seconds or less to get a result. Therefore, maybe at the runtime, the optimization program is not so good because it takes more time.
Okay, thank you.